Afternoon, all the participants. Can you check, Bhatia Saab, if its recording started? Anybody can tell me if it's working?
Yes, sir. Recording is started.
Okay, thank you very much for the feedback. So, good afternoon, all the participants, my dear colleagues, and I would like to welcome for this session our eminent speaker uh, from Belgium, uh, Mr. Philippe Arthur Jean Kilsen Chaevalier. So he's basically CEO of Lysonix BB. Please mute your mic. So I would like to welcome you, Philip, in the Department of Electronics and Communication Engineering, GB Pant Institute of Engineering and Technology, Pauri Gadwal, Uttarakhand, India. We are feeling very much proud to have you as a speaker in our faculty development program. So this FDP is of 5 days program, and every day we have 3 sessions from Monday to Friday. And we have already, this is the last session for the second day. So we are living here in the Himalayan hills, and it is very close to Dehradun. You have been to Dehradun, and 150 kilometers from Dehradun towards the hills. So the weather is very good here, and the climate is like there in Belgium. It's very clean. So now, participants, I want to introduce you, our eminent speaker for this session. So Philippe has done his Master of Science in Physics Engineering in 1984. Afterwards, he has done his Master of Science in Electronic System Design. And afterwards, he has further done the Master of Science in Photonics Engineering. And he is also pursuing a doctorate afterwards. So he is at the moment CEO of Lysonix VB, and from 1994 till date, he is also CEO of Behold IPO VB. From 2016 to 19, he was the Senior Vice President Systems ETF Mining. From 2003 to 2011, he was Project and Program Manager for OIP Sensor System. From 2003 to 2008, he was the Quality Assurance Manager, OIP Sensor Systems. And 2001 to 2016, he was Chief Scientific Officer, OIP Sensor Systems. From 1997 to 2000, he was Technical Director of Chaevalier Photonics. From 1996 to 2001, he was the member of Board of Directors of Biophotonics. From 1995 to 2000, he was the member of Board of Directors of Chaevalier Photonics. 1990 to 1997, founder and managing director of Chaevalier Photonics. From 1988 to 1990, he was the technical director of Co-Survey. From 1984 to 1987, he was the head of the Space and Industrial Optics Department of OIP Optics. He has the specialized experience in project manager and designer of electro-optics and photonics instrumentation, about more than 35 years. In optical instrumentation and diagnostics for defense, R&D, space industry, design and manufacturing of electro-optic systems for experiments during the space shuttle missions, design of optical diagnostics of the International Space Station, space qualification of electronics of CROM instruments on board of SOHO satellite. He is the member of SPIE, Optica, IEEE Photonic Society, Society of Automotive Engineers, Open Researcher and Contributor, ID, American Society of Mechanical Engineers as well. Moreover, Philippe has a wide variety of language skills. He knows Dutch, French, English, and German languages. He is also fond of Latin and ballroom dance as well. Further, I would like to tell you that he has so many registered innovations and nine registered innovations in his pocket and one unregistered innovation. He has about 11 patents registration applications, and he has been granted one patent as well. Further, if we talk about the honors and award, so laureate of the Flanders Technology International Innovation Award in 1993, certificate of appreciation for contribution to the flight of the second international microgravity laboratory IML-2 space shuttle Columbia STS-65 July 1994. So he has these awards. He has so many research publications. And further, I would like to emphasize that Philippe has contributed in our R&D projects also in India. So he has been Arjun Program Manager, GMS MK2, CPS MK2, Add-on LTD, India, Project Manager of Laser Target Designator for Arjun Tank India, Project Manager, Commander, Panoramic Site, Arjun Tank India, Project Manager of Arjun Batch 2, Project Manager of Arjun Batch 1, Supervisor of the Armored Infantry Vehicle Program of OIP. He has been production of IRBIS Weapon Sites, OIP, Gunner Main Site for Arjun Main Battle Tank India, Protein Crystallization Diagnostic Facility, Phase A, B, C, D. And there are so many its contributions, the list is, I think, quite big to pronounce everything here. And I would like to summarize in total. There are so many things I could not complete the list. So basically, now he will talk today on the topic optical systems design, and he will tell you more about the practical aspects as discussed with him today, and it's not theoretical but more practical aspects. So I welcome Philippe to our institute, to our country, and to our participants, and we feel very proud that you have given your time to deliver a talk in our faculty development program. So thank you well. And it's now up to you. I hand over the session to Philippe. Please.
Thank you very much, Sanjeev. Welcome, and we'll give today a talk on optical system design. Like Sanjeev said, it will not be theoretical, but oriented to the practical aspects of how you make an optical design from scratch. So I think I can not problem here with my slides.
Yeah, it was working before.
It was working just before. Now it's working. Okay, yeah. It's working. All right, thank you. So as Sanjeev said, this is my academic education. Some topic there is the design of the optoelectronic system for the protein crystallization diagnostics facility. That system is presently still active on the International Space Station. Another topic that is important is the work that I did for DRDO from 2003 to 2015, different tasks as project manager of the integrated fire control system. In my free time, I'm doing my PhD at University of Ghent in the Department of Numerical Analysis and Mathematical Modeling, where I develop techniques for finding laws of nature by a computer. And the title of my PhD is a mathematical classification of dimensionless quantity equations. That classification is similar to what Dmitry Mendeleev did for chemistry. I'm doing the same now for physics. It took me 40 years to discover the structure of physical quantities. But that's all my background. Let's move on the content of this talk. So I have 4 sections in my talk. The first is related to what is the information that an engineer needs for an optical design to start it. What are the tools available for him? What software could he use? What type of performance measures, once you designed the system, what is the performance of that system? And then finally, we learn by examples, and I will show you reference designs. Most of these designs can be found in the international literature, either in patents or in software tools where lens libraries are present. I will illustrate the different kinds of lens designs that exist so that you can appreciate the wide variety of systems. The systems that I will discuss are systems that are ordered from high numerical aperture to low numerical aperture. And then I close the lecture with the opportunity of questions and answers at the end of my talk. So what is the information needed for optical design? First of all, you have to think about what type of scheme will be used to, let's say, analyze the problem. And the scheme consists, in fact, of 2 flows. One is the energy flow and the other is the information flow. So we start, in fact, with a radiation source, not necessarily the source that we are looking at. We are looking at an object, but the radiation source emits an electromagnetic spectrum, as everyone knows. That radiation source can be embedded in an immersion medium. Can be vacuum, plasma, gas, liquid, solid, whatever, and it irradiates an object. That object will, if it is irradiated, give some reflection. So the emissivity, the reflectivity, the absorption, the texture of the object are important for the optical designer. Then from that object to the optical system, let's say we call the optical system a diopter, we have a transmission medium. It can be free space. In the case of fiber optics, you have guided space with different modes. And you have then as a medium, vacuum, plasma, a gas, also a liquid or a solid, whatever. The diopter can be of different types. It can be refractive, reflective, catadioptric, diffractive, hybrid, passive, active, and so on. Active, like a laser system, is an active electro-optical system. Finally, the photons hit a detector where the photons are converted to electrons, and this happens typically in CMOS sensors, CCD systems, CID, photomultiplier tube, avalanche photodiodes, focal plane arrays. Once we have the electrical signal, we can process that signal in different dimensions, 1, 2, 3, or 4 dimensions. And finally, the operator will receive some form of visualization. Most of the time it's LCD, like now the screen LCD, CRTs in the past, and then the other augmented reality and virtual reality systems. The basic optical elements needed for the start to get an understanding of the problem is that your requirements that you have will be expressed in terms of effective focal length of the optical system. Okay, everyone knows effective focal length, what it is. The F number of the optical system is an important characteristic where we have a definition given by the effective focal length divided by the diameter of the diopter of the optical system. This is a definition for an object at infinity. In case that the object is not at infinity, then you have to multiply it by a term related to the magnification of the system. Important, very important in optical design is the numerical aperture in object space. This is also related to information transfer, where we have Fourier optics that could model the transfer of information. The numerical aperture in object space is given by the refractive index times the sine of half angle, half opening angle, so theta. The numerical aperture in image space is NA prime. It's again the refractive index in the image space and the sine of theta prime. The relation between the f number and at infinity and the numerical aperture is given for the case of an object at infinity. F number is 1 over 2 times the numerical aperture. You will see that all the examples that I will explain later and give are classified in function of numerical aperture. Then, we have the famous Snell's law, n times sine I equal n prime sine I prime. What most of the time is an optical engineer in the beginning forgets that there is an invariant. It's called the Lagrange invariant. It means that the object size times the numerical aperture remains a constant when it propagates through the optical system. So at the object, you have h times NA. At the image, you have h prime times NA prime. So any system that violates this, any imaging system that violates this is not a correct system and is certainly subject to an error somewhere. Then we have a linear magnification where we have the ratio of the numerical aperture of object to the numerical aperture of the image. So be careful. For the image, it's h prime divided by h. And the optical design requirements, important is to explain what is the resolution or the performance to the optical designer. He should know what is the Airy disk, the Nyquist frequency of the system, then the bandwidth, naturally the wavelengths that are to be considered. The total field of view, you will see that in my classifications I indicate total field of view. Be careful, total field of view is not used in the software packages. They take half of the total field of view and they call it FOV field of view. So FOV, when you see it, it's the half of the total field of view. For discrete systems, it's important that you also specify the instantaneous field of view. So if you have a CMOS sensor where you have a lot of pixels, then the instantaneous field of view is the cone of light that hits 1 pixel. It's important in design considerations. On the other side, you can have requirements related to the image size, so h prime, the size of the sensor. If you have a VGA sensor or an HD sensor and so on, the number of pixels that you have there will determine the size of the image. Important in designing is that you take in account the diagonal of the sensor, not the width and the height, because in the optical system, when you do a ray tracing, you need to design for the diagonal of the optical system, diagonal of the image. Other important elements are the aperture, or where is the pupil located. Like in a telecentric system, the pupil is located at a well-defined distance from the first diopter, the numerical aperture, the f number. Other aspects are the vignetting and the transmission. Most of the people are not aware that vignetting is always present. It is a very difficult element to eliminate the vignetting. We will see that in the examples. Effective focal length, we discussed already, magnification. Then you have the mechanical interfaces. If you have your electro-optical system, you want to fix it on a vehicle, whatever, a tank, an airplane, a UAV, a car, whatever. you have mechanical interfaces. They inject vibrations, sinusoidal, shock, and so on. So your optical system should be rigid enough and should survive these external conditions. The same for temperature and temperature shocks. It's not only mechanical, it's thermomechanical interfaces. On the other side, you have the mass and the power budgets, very important in the case of an UAV. I will now indicate the different steps that an optical engineer encounters when he set up an optical system. And as case study, I take from the Oslo library. Oslo is a software package. You will see I work with Oslo. And this case is a cooled medium wave infrared, so in the bandwidth 3 to 5 micron objective. You see that the layout consists of 4 lenses. We have 2 lenses close to each other, 2 other lenses, then a window that seals the viewer where the cooling element is located. So here at that plane, you have the indium antimonide focal plane array that is located. This is a sapphire window, and it's a typical design made of 2 materials, germanium, silicon, silicon, germanium. This is the architecture. It's one design. There are many other designs. You see that the focal length of that system is 100 millimeter, a numerical aperture of 0.33. All the units are in millimeter. So an optical designer starts with defining the general conditions for the optical system. In Oslo, this is done by indicating if the evaluation mode is focal or afocal. Afocal is interesting if you have like a telescope with magnification 1, so you have an infinite, a collimated beam enters, a collimated beam goes out. In that case, you change it from focal to afocal. But most of the cases are focal. The aiming, you can center, choose your chief ray and make all the analysis with respect to the central ray. Your wavefront analysis that you performed, most of the time you take the exit pupil of the optical system. Aperture checking is switched on in most of the cases to see which rays are passing not through a lens, and so will not convey to information or energy. In some cases, you have alternate configurations, like in zoom systems. You have more than one system coupled together. In that case, it's important that solves are transferred from one system to another. The Zernike polynomials are used for decomposition of the wavefront, and you have to choose if it is X or Y as reference axis. Further, in most of the cases, we have symmetry state. It makes the calculations more efficient. But in more complex optical systems, you have to remove the symmetry and ask for non-symmetrical system. So off-axis systems, paraboloids, these are certainly systems where this should be changed to non-symmetric state. The ray aiming is typically aplanatic. Paraxial is sometimes used, but most of the time it's not there. In the case of laser diodes, you have to give information about the source characteristics like astigmatic distance between transverse and sagittal planes. The default conditions are 20 degrees Celsius and an atmosphere with a pressure of 1 bar. In case you activate polarization ray trace, in that case you have more correct approximations of wavefront calculation in the diffraction analysis. So a point spread function will be performed in 3 times. So full integration of the equations. Sometimes you can activate the image spot diagram. It allows you to have complete optimization instructions and error functions based on spot size information. You can use then modulation transfer error functions, and that can be helpful in your design process. And finally, you can indicate if you use diffraction efficiency in the case that you use hybrid optical systems like diffractive optical elements or holographic optical elements or gratings. In that case, you can activate the diffraction efficiency module. The second step is the setup of the optical system, where you have the paraxial setup. It means that you have to select what is the diameter. Well, it's the radius that you enter, the radius of the optical system. Then important is the image numerical aperture. So you can, the ones with the star indicate what you input, and the others are calculated. So in this case, the working F number, so in image plane, is calculated by the system. The Gaussian image height is given, in fact, by the size of the sensor, of the indium antimonide sensor. Keep in mind, this is H prime, but through the diagonal of the sensor. Next step is definition of the wavelengths. You can see that here this system has a central wavelength of 3.7 micron with a low wavelength at 3.3 and a long wavelength at 4.2. In the case of the example of Oslo, the weight distribution is equal for all the wavelengths. In reality, when you do the final design, this will not be the case. You have to calculate the weight distribution based on the sensitivity of the sensor, the transmission characteristics of the materials in the optical design, and naturally also the electromagnetic spectrum of the source. Also, if there is some texture and there are special wavelengths that are absorbed and not transmitted or reflected to the optics, then you have to take in account what is the impact of these materials on the weight. So this is an idealization which in real cases never occurs. The field points of an optical system, the default is that designs are made with 3 field points. You can increase that, but the standard default setup in Oslo is 3, and we take 0 on axis, 0.7, and 1 is full field. 0.7 has an important aspect in lens design theory, so we try to compensate 0.7 of the marginal ray of systems. This is an example of the optical system completely filled in with the information. First column, the surface numbers. So you have AST is the aperture stop. So the stop is located in front of the first lens. In infrared systems, this is quite common. Why? Because we want to minimize the aperture, the diameter of the first lens to reduce the cost of the lens. If the aperture here would be in the middle, then this diameter, or this the radius that you have here, the aperture radius, would be larger. You see that the material of the first lens is silicon, second is germanium, then you have again germanium, silicon, and infrared sapphire as protection window. We see here that the Dewar has a length of 20.47 millimeter. So that's the distance in the vacuum chamber where the cooled detector, so IMS, so this is the indium antimonide focal plane array that is located at that position. Further, the object height is indicated. You give also information on the title. You can change that title like you want. You see here that you have systems where you have multiple zoom. That can be interesting where this complete system is designed at an other temperature. Suppose that your system should operate from -40 to +70 degrees Celsius. Well, in that case, you make 3 zoom systems and you define in your zoom an operating temperature of -40 degree and the other a temperature of +70 degree. This is only valid in the case that you have selected the expansion coefficient for the material. Here it is air, but you have to introduce then the thermal expansion coefficient of the spacer between the first lens and the second lens. Most of the time that spacer is made from aluminum, so you have to introduce the expansion coefficient of aluminum, so something like 24.7 10⁻⁶ per Kelvin. The other elements are the silicon and the germanium. You have also to introduce the thermal expansion of the silicon and the germanium, but on the other hand, also the dNdt, so the change of the refractive index of silicon in function of temperature. So that's an important parameter so that the complete system can be adapted to the environmental conditions from -40 to +70 degree. These are conditions typical for industrial applications. Even in automotive, it goes further than that. The paraxial constants are then calculated by the system. You see effective focal length, something like 100 millimeter. Gaussian image height is given. Another element here is the Petzval radius. This is the radius located at the image space, and it has a negative radius. So the negative radius means that the image surface is concave with respect to the optical axis, what is in many cases the situation. A Lagrange invariant is there and some information about lateral magnification. Then the system is also giving aberrations. We have the paraxial ray trace where we have the chief ray data and the marginal ray data located here. Chromatic aberrations, part of third order aberrations, chromatic secondary and primary longitudinal chromatic aberrations. The sidal aberrations, it can be useful for a first approach in the design to minimize these numbers. And then once you have an optimum with minimization of the sidal aberrations, move to optimization of the optical path difference. We will see that later on. You can also, together with the sidal aberrations, go to minimization of the fifth order aberrations. So here you have spherical aberration, sphericochromatic in the other one. Here coma, astigmatism, Petzval, and distortion. Another topic that is important in characterizing the optical system is the spot diagram. So you can define the number of aperture divisions. This will define the number of rays that will pass through the system. You see that with 17 aperture divisions, we have a total of 232 rays that are transferring through the optical system. We see that we have 100% ray transmission, not energy transmission. When you see ray transmission, it's clearly no energy. Then we can find the geometric data of the spot size and compare the geometric data with the diffraction limit. So the diffraction limit is indicated here. So in units, this is 6.7 micron diffraction limit based on Airy disk radius. And you see that this is below the diffraction limit. So the geometric approach to the design is certainly not correct. The diffraction limit is larger than the geometric one. So if you would perform a geometric modulation transfer function, as you will see later, it would be wrong. You have to do a diffraction modulation transfer function to have the correct data. An important element also is the Strehl ratio. 0.99 is perfect system. Here in that system, due to the fact that we have long wavelength, it's quite easy to obtain numbers like 0.95, so 95% of the Strehl ratio. The Strehl ratio is a measure of how much energy is located in the lobe with respect to a perfect diffraction system. So if you have an airy disk pattern, you compare it, and the Strehl ratio is a measure of the area below that curve. So if you have Strehl ratio 1, then it fits perfectly with the diffraction. Here you see also some data about the optical path difference. It's a peak to valley value expressed in lambda. So here this system has a wavefront with a variation of 0.1 lambda in optical path difference. Typical optimization variables are the curvatures, the materials, the airspaces, material thickness, the tilts, decenters. Aspheric surfaces, conics, splines, the diffractive surfaces can all be optimized. And there is a lot of activity in optical design around freeform surfaces, which are more complicated optical designs, and then environmental conditions and non-optical properties of materials like thermal expansion coefficients. Most of the tools that you use for optical design have a feature of automatic error function generator. This is a type of such a generator. It makes life easier for the designer. It's like a macro, creating a lot of code behind it. You can enter different parameters. Important here is that, first of all, when you do a first round of your optical design, is that you select the RMS spot size and not RMS wavefront. So first you will correct the ray intercepts to their minimum. Once that this is done, we move to the same error function generator, but then in wavefront error. You see that you can activate the color correction method in case you have a monochromatic system, like for optical free space telecommunications, where you have a laser diode, then you select none and you have only one wavelength. You can have multiple configurations. So in zoom systems, this number 1 will be higher, can be 5, 10, something like that. You can also switch off your distortion correction when you do your first rounds of optimization. And after that, you have the possibility to modify, iterate, and put some other elements in your optimization error function. An error function gives then, for the ray intercepts, this data. You see here 1, 2, 3. The 1 refers to field number 1, 2, field number 2, field number 3. And the value of the error function is given there. The RMS value for the complete set of parameters. These are collapsed optimization functions. So you see that there are 20 operands in that. Here from 20 to 61 are here in XRMS2. And you see also the contribution of each of these error functions on the total. So the maximum, the largest contribution is coming from field number 2 in the tangential plane. You see also that the weight factor here is 1.5. We put a higher weight on the field 0.7 to converge much faster in the optical design. The error function generator for optical path difference is similar to the other one, but now we click on the RMS wavefront error, and normally you can add this one, or you start with a new error function focused on optical path difference. When you optimize the optical path difference, the mechanical modifications inside the lens systems, like positions of lenses and so on, are very small changes, not large changes. Large changes are in the mode of ray intercepts. But once that has stabilized, you go to fine-tuning, and the fine-tuning is performed by optical path differences. Here you see the error function. You can also see that with the optical path differences, the RMS error is much larger. We have still the same large contribution from field number 2. Now suppose that everything is finished, we have our design, we are happy with it, then we have to enter a tolerancing mode of operation. So in the tolerancing, you have typical default tolerances. It's labeled from level A to level D. This is typical data from the ISO norm in lens design. And you see here the different tolerances for the power fringes, 1 fringe or 20 fringes. You have also to define, when you do the tolerancing, the wavelength. So the wavelength that will be used later on in metrology to check the power of the lens. So the lens power is expressed in fringes. Typically, you have lenses with 3 fringes and 1 irregularity. Small irregularity is 0.1, so this is very high precision optics. Then on the conic constants, air spaces, typical air spaces, 0.05 is a good condition, like you see here for A and B grade. Refractive index variations, this is all typical values that you can choose. You can overrule all these elements, but it's a good guideline for high quality optics that it's used in military applications or other applications. The A-B grade is certainly a good approach. For low quality optics, B-C grade can be used as a reference. Be careful when you go from, let's say, 10 fringes to 4 fringes, it's almost exponential in cost. Tolerancing generator is a very interesting tool. It helps you to perform an inverse sensitivity. It means that if you have a lens and you change the radius, what is the impact of the change of that lens on the total performance of the system? So it's a sensitivity analysis. This gives an idea of the weight that you have to put on a certain tolerance of a surface. Like in infrared systems, the thickness of an infrared system of a lens is a very sensitive element in the performance of the system. We'll see that later on. Important is also that you select a certain spatial frequency. In some cases, for, let's say, discrete optical systems, you can select as spatial frequency half of the Nyquist frequency and then make all the analysis in your tolerancing. You can select also the number of apertures. For aspheric systems, it's best that this aperture division becomes a larger number, not 17, but something like 100, because each aspheric element has an impact on the performance. Here you see that the differential change in the RMS wavefront that was calculated, we take a value of 5 10 minus 4, and the threshold changes for giving the data. Not all the tolerance data is let's say, interesting. So we filter the data by selecting only the elements that are creating changes of 1% in the performance, in the error function. You see an output of such a system. It is an MTF inverse sensitivity analysis. This is the infrared system that we have seen with the 4 lenses. And we see that on the 4th surface, we have the largest change in modulation transfer function in the tangential plane, but also in the sagittal plane. So that one is very sensitive. And we see that the tolerance, it's a grade A, it is active on field point number 3, so it's full field, it means that we will lose almost all information, and we see that in the result here. At field point 3, we have almost nothing as information in the transverse direction. Our contrast has been reduced from 42% modulation contrast in the MTF to almost 2%. So let's say that all the information is lost at the full field if we apply these tolerances. You see also that you can indicate compensators. Here there are 2 compensators. It means that when you build the optical system in the manufacturing process, the distance between the airspace distance 9 and airspace distance 5 can be fine-tuned. And the range is plus minus 0.8 millimeter that the operator has. So it means that if you have a mechanical device there, you should see that you have different spacers to introduce. If it is a unique system, you can play with different spacers so that you can compensate for the performance. At the end of the job, you have a full MTF analysis, and then it's a go, no go, pass or fail criteria for the optical system that you have designed, built, help building. Once you have all the tolerances, you have to report that to the manufacturer. If you have the workshop in your facility, then you transfer that and you use the ISO 10010 standard, where you can indicate the different elements here in the drawing. You see here a lens with a thickness of 2.9 with the tolerances. That's the left surface, then the material specifications, and finally the right surface. The left surface is convex, the other is concave, and we have this type of lens. So this lens is sent to the manufacturer, and the manufacturer will try to produce the lens according to these requirements. Once the lens arrives at the facility, you can start doing an analysis of the surface. This is the first surface of the lens. You see this is done by a zygo interferometer. It gives a wavefront map, and you can see if, let's say, the fringes are respected. If you have the peak or valley that is given, the size, the radius, the nominal radius was 29.2. The measured radius is 29.202. It can be done by the zygo. It's not a mechanical, it's an optical measurement. And the wavelength of test, in this case, it's 546, but in many cases, it is done by a helium neon laser, and then it's 632.8 nanometer. Finally, you have also to check the coating of the lens. In this case, the specification was that at 700 nanometer, the reflection, so the anti-reflex coating performance, should reflect less than 0.5%. So this is obvious. This is the case in that design. Finally, you have a quality control. It's not one lens, but you can ask for the production of 5 lenses. Like in this case, you see the variation of the diameter, the variation of the center thickness in the production of the lens, the type of material that is there, and then the decenters that are given. And the reference is 4 fringes, 2 irregular for the zygo plot that we have seen before. So all parameters are here. The 5 lenses are passing the requirements, the test. So now, what are the tools that are available for an optical engineer? Some people design their own software for that, but it's recommended to use commercial software. The commercial software that is used in most of the cases is the Code 5 program from the company Synopsys. The Oslo, I use that one from Lambda Research Corporation for my designs. You have Synopsys from Optical System Design. Synopsys was the first software package that I used in 1984 for designing holographic optical elements. And then you have Optic Studio from Zemax. I used Zemax for designing infrared systems for automotive cars. Another tool, if you want to do physical optics designs like Mach-Zehnder interferometry and all that stuff, then it is better to use the software tool Virtual Lab from Lighttrans International in Germany. Now, okay, we have done a design. How will we measure the performance of the designs? The performance of the design is typically given by optical transfer function. This is a complex function, so the OTF contains two parts, a modulation transfer function, which is a real part, and a phase transfer function. The phase transfer function can be important in the case of coherent illumination, coherent imaging. Classical element is also the point spread function, where we have the airy disk for incoherent light. This is the equation. The spot size in incoherent is given in function of the wavelength and the effective focal length and the diameter of the system. And naturally, the cutoff, you cannot transfer more information than the highest frequency in information given by 2 times the numerical aperture divided by the wavelength. When you do or when you design an optical system for any type of system, automotive, important is what is the range, up to which distance can I look. It's not infinity. In most of the cases on real Earth, we are looking at distances like 100 meter, 300 meter, 1 kilometer, and so on. In that case, it's important that you know the aerial image modulation of the detector. In fact, this is a curve that gives the minimal contrast needed to observe a certain frequency modulation in the modulation transfer function. So it is a curve that you have to superpose on top of the MTF, and the intersection of the aerial image modulation function and the modulation transfer function gives the full picture of the performance of the optical system. We have seen this system. We will go through the details of that system. That was the case, the study case. Now the ray intercept curves. We have here the 3 fields that we see. That part is the tangential part. This is a sagittal part. So an optical designer looks first to this type of graphs to see what is the aberration. And you see here the wavelength, the color is giving. The green is the central wavelength, then the blue one is the short, and the red one is the long wavelength. You see here some interesting feature. The green one here closes here on the axis, left and right. It means that you have a peak error at approximately 0.7. And that's the reason why we put in our error function a higher weight at the pupil position of 0.7. So 0.7 is 0.7 is 70% of the diameter of the optical diameter of the diopter. So if you want to influence the high frequencies, you have to put a higher weight there, and this is done. It is compensated, so we will have a good
Hello. Badaiyu Dr. Saab, officially Dr. Saab.
Thank you. Yeah. Then you see here the astigmatism and
last में बस
and the chromatic
from my side तब मैंने leave किया था.
There is a low distortion here and a lateral color. The distortion analysis here is given. We see clearly a pattern here, and you give this part. There is a a low distortion in that case, 0.2%, lower than that. And here you see no pin cushion and no barrel distortion. So it's well balanced, well corrected from the point of view of distortion. Now we look to the modulation transfer function. It's a polychromatic modulation transfer function where we have the different weights for the 3 wavelengths. You see clearly here the top line that is here is the perfect system, diffraction limited, so higher than that you cannot go. This is the physical limit. So you see that we have here a variation. This is typically an error of the order of lambda over 2 for this type of system. We have 200 millimeter, 200 cycles per millimeter as cutoff frequency for the system. So we see that there is some improvement possible in that system. The system doesn't contain aspheric optics and doesn't contain diffractive optics. If you would introduce aspherics and diffractive elements, you can boost the performance by closing this gap. So this area can be compensated by introducing the aspherics and also diffractive elements. We will see some examples of these designs later. Here you see through focus modulation transfer function. So at 0, you have the plane of the detector, the indium antimonide detector, and you see the variations. If you do a defocus, then you have an impact on the performance of the modulation transfer function at the given frequency of 40 cycles per millimeter. Another important element is the point spread function in the analysis of the performance of the system. Here you see that the peak is located at 0.54, so we have 54% of the perfection is in that system. So there is still work to do in that optical design. On the other side, if you have a discrete system, it's also interesting to know how much energy is collected by the pixels. Here you see the system. The pixels of the detector are typically 15 micron pixel pitch. So we take here on the axis 30 micron. It means 2 pixels. So we have a square of 2 by 2. So in total we have 4 pixels. And in these 4 pixels, we have this amount of energy that is collected. So we have approximately 90% of the energy of a point object is collected by an array of 2 by 2 pixels. Line spread function is interesting for the designer, but also for the experimenter, because when you do a test of an optical system, scan systems are used sometimes. And in these scan systems with very small slits, you record, in fact, a line spread function. In some configuration, you have also a knife edge as a test, like in visible systems or in astronomical telescopes. Knife edge is also very interesting. Using Fourier transforms, you can transform this to modulation transfer functions. Then you have also the wavefront map. The wavefront map here flat. You can see that the peak to valley OPD is 0.1 lambda. This is for the central wavelength and on axis. Here you see the same information, but then in 3D. So you see that you have a concave wavefront with a peak of 0.1 lambda here at the edges. In the central part, it's quite flat, and this is okay. That wavefront can be transferred naturally to numerical data for further processing, and also can be used for comparing the design with the Zernike coefficients that are obtained by the ZIGO interferometer. So you can compare this with the ZIGO or introduce this in the ZIGO and then compare the deviations from the nominal design with the really produced as built lens system. What are reference designs? Well, there are libraries containing 1,000 different lenses. You can buy that, study these different designs, and use them as starting design. First, you have to find in which category you should look, and there it is the numerical aperture that will help you. The numerical aperture is a very good classification parameter, and you start with that. Then the next step is to see what is the field of view. So once you have selected, suppose a numerical aperture of 0.5, then you say, well, I want a field of view of 10 degrees. You select that in the different libraries, and you get then an optical design. Hopefully, the optical design is in the right wavelength band, and then you start designing from that element. Be sure that no one of these libraries give you the final answer. So you will have to work and work hard to find a solution that meets the requirements of your customer. First example is a microscope objective for the visible. It is a microscope objective without cover glass. So classical microscope have a cover glass of 0.17 millimeter, but this gives you an idea of the complexity of what you can find in an optical microscope. This one has a total field of view of 22 degrees and a high numerical aperture of 0.92. It has been scaled to a focal length of 100 millimeter. Another one with a high numerical aperture of a totally other family is an uncooled long wave infrared, so in the region 8 to 13 micron objective, consisting of 4 lenses, and there is here a cover glass in front of the microbolometer that is used for the uncooled infrared system. It has a total field of view of 20 degrees and a numerical aperture of 0.1. Here, it's not important to consider Narcissus effects because it's a microbolometer, it's not cooled. You see that in this design, the designer has selected the pupil inside and not in the front. If you would move this part to the front, then you reduce the size of the front lens. So if you start with that design, then a designer would opt for cost effectiveness to move this towards there, but then naturally there will be more complications in the aberrations of the system. Another type of family is a compact disc player, pickup lens. Here you see an example of an aspheric lens. This is the compact disc, the polymethyl methacrylate plate. Here is the information that should be read by the system, and here the surfaces are both surfaces are spline functions. And this is a system that operates at a laser diode wavelength of 780 nanometer. You see that the focal length is very short and it has a large numerical aperture, but a very small total field of view. Many people know the Barco projector systems in conference rooms. Well, if you want to know how these things are built, this is a typical design of a red, green, or blue projector element. These are quite large optical systems. And here you have the CRT tube for the old ones. LCD projectors are not like that. They have other designs. And in some cases, you need here to cool the CRT. So you have a flow of water or liquid, not water, a liquid flowing through the system, creating sometimes problems. So these are complicated optical designs. The numerical aperture is 0.56. All the lenses here are made from plastic material. And so it's not glass. These are not glass lenses. You have a total field of view of 50 degrees for that system. A very complicated design is this one. It has a long focal length of more than 2 meters. It is used in UV lithography. It's operating at 248 nanometers, so in UV spectrum. And you see that a mask that is produced, a large mask, is reduced by that system to a smaller one. So here you have your target where you want to perform the irradiation on the chip and to make your chips. You have to reduce this from there to there. Complication there is in fact the ghost that can occur. The stray light in these systems are very important because you hit this with a lot of energy, and so this is important feature, stray light analysis for these systems. This is a Biotar objective. It contains 3 singlets and 1 doublet. It has been derived from the classical triplet system. And here you see already the first impact of vignetting. Look at the number of rays that are here and the number of rays that you have on axis. So part of the energy will be cut off by the lenses. And so it means that you will have in the detector plane here a variation of irradiance. So the irradiance will change due to vignetting effects. The field of view, total field of view is 14 degree. So normally we want a larger field of view, and we will see that in the next design, how this is done. You move from the Biotar to a double Gauss objective, but this is at the expense of a higher vignetting. You see clearly the width of that beam is much smaller than the width of the green beam, so a large variation in irradiance in the plane, but you have a much larger field of view, total field of view of 44 degree in that case. This is the archetype of optical designs used in camera systems. This is another family. It's an eye-safe laser rangefinder, miniature eye-safe laser rangefinder, operating in the telecom wavelength of 1.55. So it's a laser diode that is located here. The object at infinity is located in object space. This system is based on sending a circular polarized beam to the target. The reason in that design for using that is to eliminate polarization effects that are present by reflecting targets. If you have a circular polarized beam here, you will have less impact of scattering in the atmosphere. So a signal noise ratio of your eye-safe laser rangefinder will be higher. The design consists of 4 lenses. The lenses are cylindrical, and they are made of a certain material that is optimum for operating at 1.55 micron. Here you see the other side where you see the cylindrical lenses located there. The key element here is where do you start the design? On the right side or on the left side? In 99% of the cases, an optical designer will start from the source. It means here a laser diode. And you will see that in different books that they make the design starting from the laser diode with the astigmatic elements. In this design, it's the design that I made for my master thesis, this one starts from the object. And the important element is that you design the rays in such a way, or design the lenses in such a way that you couple the light like a waveguide. So you assume that here you have a waveguide, and you can then couple this radiation inside it. And naturally, due to the astigmatic features of the laser diode, you have different focal lengths. You have a focal length of 17 millimeter for this one, and a focal length of 9 mm for that one. Another family are head-up displays. You encounter them in advanced cars. My Volvo car has such a head-up display. It projects information. It's not a CRT, but an LCD, and it projects this in front of the operator. These things are sometimes built on a windshield of a car. You can have it also on a combiner, like for fighters, airplanes. You have this also. It's a complex design to get it in the correct way. Here you have an uncooled long-wave infrared objective. This one has here another window. It's between 8 and 12 micron. And you see here that the aperture is located again in the middle of the optical system, a numerical aperture of 0.5 and a total field of view of 18 degree. This is another uncooled long-wave infrared system. It is a molded diffractive objective. It is introduced in the BMW 7 cars. It is the thermal camera of the BMW. I participated in the design of this system. It constitutes two molded elements, both made from gazier. Gazier is a special infrared material. It's a chalcogenide material, so a ternary material, and you can mold it. This gives here a system with a numerical aperture of 0.45, so f number 1.1 approximately, a total field of view of 24 degree, and an effective focal length of 19 millimeter. I designed this system using Zemax. This is design of a biocular. Biocular is a special eyepiece. It is complicated in writing the error function due to the fact that you have to take into account the position of the pupil of your left eye and the right eye. And both eyes are concentrating on one object. So you have, in fact, two images that are combined. And most designs are done like here at infinity. So if you if you build this one, you will have a headache as observer. If you want to compensate that in the object space, you should introduce a diopter of -2 dioptry. So -2 diopter in that space will compensate for problems with the physics of the eye, and then you don't get headaches. So these are complicated systems. Don't think that this is designed in 1 month. Digital camera. For a digital camera here again, clearly see the vignetting problem. So the long variation, the big variation, in irradiance. It's total field of view of 36 degree, numerical aperture of 0.42. You see that this is already a variation on the double Gauss, where the aperture is located here, but there is more weight distributed here on the first part of the lens of the objective than on the other. So it's not a symmetric distribution of lens power along the pupil here. That's another type of projector. This is a projector objective, like for an LCD. You can project the system in that way. Total field of view of 18 degree and a numerical aperture of 0.42. You see again typically the doublet structure with two meniscus lenses in front and then two other lenses. Here a meniscus lens also close to the sensor, to the LCD plane. Here, let's say the glass plates are not indicated. Another type of family are reverse telephoto objectives. These have a special property. The focal length of that system is 100 millimeter, but the physical length of it is many times 100 millimeter. It's a reverse telephoto. A telephoto makes it shorter. A reverse telephoto makes the mechanical dimension of the system longer. There's a total field of view of 26 degrees and a numerical aperture of 0.42. Observe that you have here a plane that is placed there. This is a plane where the diaphragm is located, and it is located very close to the front focal length of this group. And by doing this, you create an almost telecentric system. You see that the chief rays in red, green, and blue are almost perpendicular to the detector plane. This is an advantageous configuration due to the fact that if you have slight variations in position of lenses or in tolerancing, the magnification remains the same. There is no change with the position. The relative position of the image height here and there remains the same if you move that interface to the left. This is not the case in classical designs, like in this one. You see it clearly. It's under angle. There it's also under angle. Modification of the position here of the LCD will change the magnification. Other family, a catadioptric objective. This is interesting. It's a combination of mirror system and lens system. The disadvantage of these systems is naturally the big obscuration that you have there. The advantage of it is that you can create very compact optical systems. Suppose you need that for a night vision goggle with long range, then this is the preferred design. So you have the weight distribution, handheld night vision goggles. Well, this type of design is used. Total field of view of 10 degrees and a numerical aperture of 0.41. So you see we are now a little bit further than halfway in numerical aperture. This is a helicopter pilot night vision objective for visible near infrared. There the difficulty in the design is to have near infrared and visible. So the cockpit information should be visible by the pilot. And at the same time, the night information from the near infrared should also be available. So this is a 40-degree field of view with numerical aperture of 41 and an effective focal length of 24 millimeter. Why 24? Because the pilot should have a magnification of 1, and the human eye has typically a focal length of 24 millimeter. So you need an objective with 24 millimeter, you need an eyepiece of 24 millimeter, and then you combine that all together. You have then an overall magnification of 1, and you see everything in the real world at the right scale. This is a cooled medium wave infrared system. Here we have again the Dewar. We discussed that. That was one of the cases, the study cases. Here you see a zoom objective from Nikon. Here you see two parts, two elements that are moving together towards each other. That part remains fixed at the end. And then you can see that you can create a 12 times zoom objective with field of views changing from 49 degree to 3 degree. For telecom operations, you can use a free space telecommunication with laser. You can use a Gregorian mirror. That's one of the systems. But you can also have other optical systems that are less big than that. Like this one is not a mirror, but it's a laser-free communication objective at helium neon laser wavelength. with a numerical aperture of 0.25. The typical geometry there is a doublet that you have and then a meniscus. By putting the meniscus, you increase the flatness of the field and you improve the spot size with this meniscus. This can be a simple exercise. Take a doublet, look at the spot size, put a meniscus lens, so an accompanying meniscus lens, and then you reduce it to a spot size of 3 micron, 5 micron, even less. Another interesting objective is a mirror objective. Also for telecom observation, you have a Schwarzschild's microscope, where you have a collimated beam and then focusing here in a small spot. For biology, you have the reverse configuration, where the object is located here and you magnify it. So then it's a Schwarzschild's microscope objective. Interesting because that system allows to use other wavelengths and it's not limited by the materials like glass materials. It is a mirror microscope at that time. Well-known system is the Cassegrain mirror objective. It has a concave mirror and a convex mirror to make it shorter and compact. A variation on this Cassegrain mirror objective is the famous Richer-Chrétien mirror objective using aspheric surfaces, but it's also concave and convex mirror. So the issue there is, again, for all these mirror objective is the obscuration ratio that is there. But for telecom, it can be a very interesting application because there is no dispersion in that system, no element of dispersion in the mirror designs. Here you see a design of a cooled dual field of view objective, long wave infrared from 7.5 to 9.5 micron. This is the wide field of view of the system, and that's the narrow field of view of the system. One has a field of view, total field of view of 10 degrees and the other 4. The mechanism for going from wide field to narrow field is that you rotate this pair of lenses outside of the beam. So you rotate it by 90 degrees clockwise, and then these lenses disappear and you obtain this system. What is common to the systems is this part, which we call then an eyepiece, because you have an intermediate image plane located here. You don't have to optimize this image plane. It's the total system that should be okay. But when you start this type of design, you should not start from the left and go to the right. Because if you do this, then this lens, the last lens, will be concave and not convex. And if you have a concave lens in a cooled system, you can be sure that you have narcissus. A narcissus is a black dot in the middle of your thermal infrared image. So you can enforce this by starting from the right side. You start from the detector, not from the object. You start from the detector and you send here the light through the cold stop and then try to devise the eyepiece in such a way. You force the first surface here to keep it convex, and then you optimize for this intermediate plane. Then you reverse the system and you continue by having an afocal system at the left side, and you optimize it again on that side. Naturally, this should be completely analyzed in athermal mode from -40 to +70 degrees. This is an example of an extreme optics. You have a fisheye objective with a total field of view of 175 degrees. You see here the field of view entering through that system. A classical objective in mobile phones is a tessar, but some designs now have aspheric surface and free space, free surface lenses here. So this is a classical design of a tessar. CCD objective for near-infrared application. Here you see the design. It's going from 0.76 to 0.79, so very short bandwidth. Again, a derivation of the Gaussian design. Important for hyperspectral imaging is this geometry. It's a 3-mirror objective. It's a 3-mirror anastigmat that is used on satellites for hyperspectral imaging of the Earth. And this is an Ebert grating monochromator. So you have here a slit, and it goes to a grating. The grating split the electromagnetic radiation in different bands. And here you have output slit, exit slit. It gives you a possibility to analyze the wavelengths. This is another cooled medium wave infrared. It's an athermal low distortion objective. This was designed specially for automotive applications, for cars and trucks, designed from the left side to the right side. Visible system, athermal and low distortion. This is the system that you have here with a numerical aperture of 0.08. Also, athermal is from -40 to +70 in this design. An example of an eyepiece. This was for the helicopter night vision goggle. Here you see the system, and the spectrum there is a P43 phosphor. You see that the image intensifier tube has a curved surface, so you design for that curved surface. That's the position of the eye of the observer, so you have a certain eye relief for the comfort of the pilot. This is a visible system for autonomous vehicles. It's again athermal and low distortion objective with a larger field of view of 54 degree. And this is an athermal low distortion objective, again for autonomous vehicles operating in the shortwave infrared. It's important to design that. Tesla has not a shortwave infrared objective, but should have such an objective to be able to look through fog and also scattering effects that impair the visible channel. Total field of view of 9 degree, numerical aperture of 0.08. So this concludes my lecture, and I'm open for questions, and I hope to give the answers. Thank you.
Thank you, well, Philippe. It was very, very super, excellent lecture, and your energy was really a constant throughout the period from 2:30 p.m. to now 4 p.m. around. It did not attenuate in due course of time, actually.
Yeah.
Yeah, so very nice and informative lecture. And I'm also getting messages on the WhatsApp group that it's very good session. Now, this is the question answer session. So I would like to request the participants if they have any queries and any doubt. You want to ask some questions. So Philippe is here with us and you can ask.
Sir, my one question is.
Who is there? Who is there?
My doctor.
Please pronounce your name and then you can ask the question, okay?
Philippe, good afternoon. Myself, Dr. Kirit Semwal. I want to ask how you convert this eye-shaped laser.
How you convert? It's a laser diode of 1.55 micron. So like I showed you. I don't understand your question. What do you mean by convert?
Which crystal you have been used for optical parametric oscillation for converting this eye-shaped laser?
No, it's a laser diode. It's a laser diode.
Yeah.
It's a laser diode. Okay. It's not an Oppo. It's a laser diode, and the blocks of glass that you have seen in the middle are a polarizing beam splitter. Maybe I can move to very fast to the slide. Here. Here. So that part here. Oh, sorry. That part here is a beam splitter cube, polarizing beam splitter cube, where you have here a lambda over 4 plate. Due to the linear polarization of the laser diode, you can use a lambda over 4 so that you transform linear polarized light to circular polarized light. Then it comes back, reflected back in the receiver. The receiver channel is not shown, but it is then decoupled here by the polarizing beam splitter to the receiver channel, where you have an avalanche photodiode as a detector.
Okay, sir. Thank you. One second question, sir. How to measure the transverse electromagnetic mode, TEM00? How to find?
It's not TEM00. It is it's a multi-mode, high power laser diode in that design. So I don't remember by heart. It's an Hermite mode. What was it? 1-1 or something like that. I have to look in my master. It's from 2015. I don't remember exactly the mode of operation of the laser diode. It's a commercial laser diode manufactured in Canada, and that laser diode can be used for this application.
Okay, sir. Thank you.
Yeah, thank you, Dr. Samuel. Any other participant, if you want to ask a question? If you have any doubt, you can ask Philippe. No? Yes, Nidhi Singh? Yes, Nidhi, please ask your question. You can unmute first and then you can ask. Yeah.
Good evening, doctor.
Yeah.
Yes, you can.
I'm a research scholar in IIT Kanpur, actually. So I'm designing a WDM system. Hello.
Yes, please ask your question. We are listening.
What are you designing? Wavelength division multiplexer.
WDM system.
Yeah.
So it's with the help of WDM multiplexer. I'm using certain transmitters at n number of wavelengths.
Yes.
And after that, I need to analyze the performance analysis of the WDM system. So in terms of bit error rate or OSNR, and
you
in
need
the performance analysis, I'm using optical fiber as a channel.
Yes, okay, but at the end you are.
Can you help me in determining what all, apart from the dispersion and attenuation, are there any other specific parameter which I can consider in my analysis?
Yeah, first of all, I assume that at the end of the story, you have a situation where, let's say, here you have a fiber optic, where you have a certain spectrum. This is, in fact, your wavelength division multiplexer, where you have different wavelengths. And then here you go again to free space, or are you coupling it in a fiber?
I'm coupling it in a fiber.
Yeah, okay. Then it's important that you use a mode analysis, because if you are in free space, you can use modulation transfer functions and all that stuff, equipment. But here you have to consider what happens in a guided wave. It's a guided wave. So it is guided at the source and it remains guided to the detector. So in that case, you don't have the situation like I showed for, let's say, classical Fourier diffraction and all that stuff. You have to do the performance analysis based on propagation inside a guided mode. So the modes should be analyzed. And then it depends on the characteristics of your optical fiber. You have there different types of propagation. If I remember, it's something like Laguerre modus and all that stuff. They should be considered.
So one more question.
Not Fourier optics, because they don't interfere. Naturally, if at a certain moment you have a fiber located here, then free space, and then a fiber there, then this part is free space. Then you have to use modulation transfer function and monochromators and all that stuff that you have here. Once you leave the fiber, you have free space, and your modes are totally...
Are you talking about free space channel?
Yes, if you have a free space channel, you have a transmitter and a receiver, then in free space, everything what I explained here is applicable.
Okay. For so my case, if I'm designing
that is a fiber or an LED that couples or laser diode to a fiber. If this is the exit pupil, in fact, of the fiber, then it propagates through free space like the normal Fourier optics that you can use.
Okay. So can you help me in determining the tools which I can use for that free space optics? The same tool which I'm using for optical fiber, can I go for free space optics also?
Let's say if you use the tools from I will show the different companies again here, because Oslo has some fibers, but I would not recommend that. We should use, I think, the virtual lab, this one, virtual lab, light trans. This, I think, this is the good approach, because with that tool you can combine modes that are emitted by an optical fiber, then couple it to. Sorry.
Can you please pardon?
You can buy that. You can buy that. Light Trans International is a company located in Germany. It's a spin-off from the University of Jena. University of Jena in Germany. Okay. And the lead scientist there is Mr. Witkowski, and I think it's also Witkowski. I think it's the name.
Okay.
Yeah.
So I can have an access.
Yes.
So please. I can have an analysis on the basis of both optical fiber as well as free space optics.
Yes, with this one, it's a physical optics tool. It will combine your fiber optic characteristics with the free space characteristics. The other are ray tracing, and that's not the right way to represent the electromagnetic radiation, because you start from modes in an optical fiber. So there you need to do it in another way. Start using virtual lab. I think it's around 10,000 euro, the software.
Yeah. That's perfect. And I would like to add, Nidhi, for you, tomorrow, I don't know exactly, maybe tomorrow, Dr. B.C. Chaudhary from NIT Chandigarh, NITTR Chandigarh, he will also deliver a talk on FSO, actually. If you are talking about FSO, yes, so you can also ask him the question related to FSO. Then maybe you can have more idea what kind of instruments you can use, right?
Okay.
Chaudhary sir will deliver the talk in coming days. Okay, Nidhi. So we have another question. Where is Sandeep was asking question.
Ich habe eine kleine Frage. Sorry.
Hello, Sandeep. You raise hand actually.
Can you hear me?
Yes, you are audible.
One of the questions I had was already asked by Nidhi.
You can first you can tell your name and where you are at the moment. That's fine.
I'm Sandeep. I'm working with Shankar Kumar Selvaraj, who gave a talk today morning. I was with Sanjeev for a long time in Ghent. Like we were sitting next to each other doing our PhD. I never finished.
Yeah, he's working on projects at ISC Bangalore actually with Shankar.
Yes. I was in Ghent University for more than 4 years. So yeah, Philippe, one of the questions, the answer was virtual lab. But what another small question I had was the chalcogenide you were mentioning. What is it called?
Sandeep, your voice is not very clear. Please, there is some noise in the background.
The chalcogenide that you are using.
Yes.
That is Gazir.
Gazir. It's made by Umicore. It's the Gazir 1 that I used for the thermal camera of the BMW. I can talk about that because my non-disclosure agreement is okay, finished. It's more than 10 years ago. Design was 10 years ago, and that was for BMW 7 series. And I made that design together with a designer from Umicore located in France. So we worked with chalcogenide glass. It's the Gazir. It's a Umicore material, and it was Gazir 1.
Thank you. Yeah, I think it was a very nice talk. I mean, I don't need to say it, I think, but because everyone knows it. But it was very, very informative because the way you were mentioning the applications that were directly there, I think that gave a very, very easy people who were listening to the talk could understand or could get what you were talking about very easily. So that was very nice. Thanks a lot, Philippe.
Thank you. Well, the difficulty in the design of the one that I showed here, the molded diffractive objective, it's more complicated due to the fact that you have to create something that can be removed from the mold. So here you have aspheric and diffractive surface. This one is an aspheric diffractive. That's aspheric, and aspheric. Okay. So, and the problem is the thickness, the ratio of the thickness to the diameter of the lenses are limitations in the manufacturing process. So if you want good quality of lenses, it's not only a good image, it's also the manufacturing process behind that design that has to be taken in account. So we could create a better optical system, but it cannot be manufactured by molding techniques. You see? So that's the challenge. That was the challenge 10 years ago.
Yeah. So yes, thank you. Any other participant? If you have any query, please ask if you have any doubt. Okay, Philippe, I was also curious to know one thing. I was thinking from long time back, and then today I came to know about your like in-depth knowledge about lenses and all that. Many times I thought that why we cannot have the tunable eyeglasses.
Tunable eyeglasses. Well, they designed one. They designed one in Ghent at university. There is a spin-off company that has an autofocus glasses. So they started this year with their company. The spectacles cost €1,000, and well, the government in Belgium is now compensating these spectacles for 150 or 140 euro. They are very advanced, and it's a spin-off from the University of Ghent. They are the first in the world who created, in fact, adaptive autofocus glasses.
Oh yes.
So I hope I will be able to buy one set because I have multifocal
lenses.
Difficulties with my spectacles, reading computer. In total, I have 4 spectacles. One for reading.
I was thinking many times like this.
Reading the computer. one for looking at medium distances and driving a car. And then when I drive the car for a long time, I have glasses that are tuned to infinity. But then I cannot read my dashboard anymore. But it's more relaxed. So autofocus spectacles could help me. But they cost, 2 times the price of a normal set.
Okay, and do you have idea what technology they have used in this? Any idea?
I don't know. It's from the micromechanical department, where the lab is located there. I don't know exactly the guys. I've seen his name, forgotten his name now, but he was teaching. Practica or something like that. I've forgotten. But you can find it on the internet. You can find it on the internet.
Yeah.
So they are able to modify the lens by micromechanical devices.
Yes, so that we can tune it for long distance and short distance like this.
Yes, yes. Quite interesting, really.
Yes. I was thinking once that why we should have 2 lenses.
Big achievement.
Yes.
Big achievement.
Yes. Okay. Any other question from the participants? You are most welcome to ask questions. Philippe is here with us, and really we are interested to know your knowledge as well as different aspects of lenses. No questions? Okay, so very excellent answers, Philippe. What you explained, I really liked the way you explained in depth with the practical aspects of the things, and also my doubt for so many years to develop about tunable lens. I was thinking, and you cleared that already. People have worked on it, so okay, that's nice.
Yeah.
Okay. So thank you very much to spare your time with us, and it's more than 2 hours now. Not more than 2 hours. Yeah, more than 1.5 hours. So very informative talk and very high level of energy. So thank you very much.
Yeah, and thank you. Thank you, Sanjeev. Yes, and I hope that I once will be again in the region of Dehradun, and okay, my ex-colleagues from IRDA will probably welcome me from the RDO also. Okay, bye-bye, Sanjeev. Bye-bye, everyone there. Thank you for listening. And it was my pleasure to give this lecture. Thank you.
Thank you, Philippe. Thank you. Bye. Have a nice evening. Bye.